Hi everyone, welcome to AI Crack channel. This is Akash Gangwar and today we'll be studying Progression Lecture 2. So we'll be studying properties of AP and basics of GP in this lecture. So let's begin our lecture with the properties of AP. So the first property is if A, B, C are in AP, then we can say that 2B equals to A plus C. That's very simple and commonly used. Okay. So let's say A, B, C are in AP. Then we can simply say that B minus A would be common difference. Also C minus B would be common difference, right? So basically B minus A equals to C minus B. That would give us 2B equals to A plus C. Very simple, right? And now if we talk about considering numbers in AP, then it's actually not a property, but we have to understand how to consider numbers in AP. Why? Because that would help us in problem solving, right? So the first point is if there are three numbers in AP, then assume A minus D, A and A plus D. Why? Why not the standard one, A plus D, A plus 2D? So let's see that with an example. So let's say there is a question where it's been given that we have three numbers which are in AP and their summation is 9 and let's say their product is 25, right? So let's take the standard one first. So we have A plus D and A plus 2D, right? These three numbers are in AP with the common difference D and first term as A, okay? So if we write down the summation over here, we'll be getting A plus D plus A plus 2D equals to 9. This is our first equation. Second equation would be A times A plus D multiplied by A plus 2D equals to 25. This is our second equation. Now with the first equation, we'll be getting a relation between A and D. In the second equation, we'll be getting a cubic equation in A, right? So it becomes very difficult to solve, right? Agreed? Now let's take the suggested method. So what we are doing over here, we are taking the first term as A minus D, second term as A, and third term as A plus D. Again, common difference is D over here, but first term is changed. First term is A minus D over here, okay? Now if we write down the summation over here, we'll be getting A minus D plus A plus D equals to 9. Now you can see that D gets cancelled out. What we have got? We have got 3A equals to 9. So A equals to 3, right? So this is directly given as the value of A, right? Directly solved for one variable out of these two variables. Now you can utilize this A to find out, to use this equation to find out the value of D, right? Simple. Similarly, for the second point, if there are four numbers, then assume A minus 3D, A minus D, A plus D, and A plus 3D. Why not A minus 2D, A minus D, A plus D? In this case, there is no symmetry because if you again do the summation, D would not cancel out, right? D would not cancel out, so that's why it won't be providing any kind of symmetrical advantage. So that's why to understand, to make it more symmetrical, we'll be using A minus 3D, A minus D, A plus D, and A plus 3D, right? But mind that here common difference is 2D. So if they're asking in question, okay, find out the common difference, you don't have to report D. You don't have to report D. You have to report 2D, right? 2D is the common difference and not D. So just make sure that you are understanding that common difference over here is 2D. Okay. And now let's talk further about the properties. So we have the sum of terms of an AP equidistant from the beginning and end is constant and equal to the sum of first and last terms, right? So what do we mean by that? Let's say the first term is A, second term is A plus D, third term is A plus 2D, fourth term is A plus 3D, fifth term is A plus 4D, sixth term is A plus 5D, and seventh term is A plus 6D, right? So this is T1, T2, T3, T4, T5, T6, and T7, okay? Now, what does the property say? It says the sum of terms of an AP equidistant from the beginning and end is constant and equal to the sum of first and last terms, right? So, what is the sum of first and last terms? That is T1 plus T7. That is A plus 60. That comes out to be 2A plus 60, right? This is the summation of first and last term. And what we have to do, we have to go equidistant from the beginning and the end. So let's say we are moving 1 unit from the beginning and also 1 unit from the end. So what we have got T2 and T6. So if we add T2 plus T6, what we'll get? We'll get A plus D plus A plus 5D. What we have got? We have got 2A plus 60 once again. So we can see that when we are going equidistant from both the beginning and the end and adding those terms, we are getting the same summation as the first and last term, right? Simple. So if you add T3 plus T5, you'll get 2A plus 6D. If you add T4 two times, you'll also get 2a plus 60. Okay, why 2 times? Because we're going 3 units here and 3 units here, you'll arrive at T4 only. Okay. Now the other property is every term of an AP is average of terms equidistant from it, right? So what does it mean? Let's say we are taking a term T4, right? So it is saying that T4 is the average of all the terms which are equidistant from it, right? So if we go 1 unit here and 1 unit here and add them and take the average of both these terms, we'll get T4 as the answer. So let's do that. T4 equals to A plus 3D, right? Now what we have done, we are going 1 unit over here and 1 unit over here. So we have got T3 plus T5 and we have to take the average, divide by 2. That would give us T3 is A plus 2D, T5 is A plus 4D, divide by 2. That gives us A plus 3D only. Okay, let's take one more example. Let's say we're going two units, right? In that case, what we'll get? We'll get T2 plus T3 plus T5 plus T6. Let's take the average, that divide by 4. That would give us A plus D plus A plus 2D plus A plus 4D plus A plus 5D, divide by 4. We have got 4A plus 3D and 7D and 12D plus 12D divided by 4. We'll still get A plus 3D as the outcome. Okay, so these two properties are very important. And now let's talk about this property. So if each term of an AP is increased, decreased, multiplied, or divided by the same non-zero number, then the resulting sequence is also an AP. Okay. So let's say we have 2, 4, 6, 8, 10, 12. Basically an AP with 6 terms, right? Let's say we add 2 in each term. What will be getting? We'll be getting 4, 6, 8, 10, 12, and 14. Now you can see that this is also an AP of 6 terms with a common difference of 2. So common difference is not changing, right? Common difference is same when we are adding a same number in every single term, right? Now same thing can happen if we subtract something over here, right? So if we are subtracting 2 from here, we'll be getting 0, 2, 4, 6, 8, and 10. Now you can see that this is also an AP with the common differences too. So when we're adding, subtracting anything, common difference is not changing, right? Common difference is not changing, but we're still getting an AP, right? Now let's say if I multiply 2, right? Now what we'll get? We'll get 4, 8, 12, 16, 20, 24. Now you can see that we have got a common difference of 4 in each term, right? So in this case, common difference also got multiplied by 2. In addition and subtraction, common difference was not changing. Although we got a resultant AP, but common difference was not changing. But in this case, what is happening? Common difference is also getting multiplied by the same number with which we have multiplied the individual terms, right? And now let us solve this question. The sum of three numbers in AP is 27 and sum of their squares is 293. Find them, right? So that's a very standard problem, right? So when we have to assume three numbers in AP, what we do? We choose A minus D, A and A plus D. Always. Don't go with A plus D and A plus 2D. Always go with A minus D, A and A plus D. Okay. So summation is 27. Basically, that means A minus D plus A plus A plus D equals to 27. So D gets cancelled out. What we have got? We've got 3A equals to 27, A equals to 9. We have got A equals to 9 over here, right? Now the question says sum of their squares is 293. So A minus D whole square plus A square plus A plus D whole square equals to 293, right? Now A is basically 9 over here. So what we have got, 81 plus D square minus 2AD plus 81 plus 81 plus D square plus 2AD equals to 293. 2AD gets cancelled out. Now what we are left with? We are left with 3 into 81 plus D square, basically 2D square equals to 293. Now this is 243 plus 2D square equals to 293. So when we subtract this over here, we'll be getting 2D square equals to 50, D square equals to 25. That gives us d as plus minus 5. Okay. Now the terms can be 9 minus 5, 9, 9 plus 5, or 9 minus minus 5, 9, 9 plus minus 5, right? So these two possibilities can be there for the terms. Okay. And now let's solve this question. If the summation is 693, where A1, A2 till A21 are in AP, then we have to find out this summation. Okay. So what we have been given is A1 plus A2 plus A3 plus till A21 equals to 693. Now let's say the first term is A over here and common difference is D. So A1 becomes A, this becomes A plus D, this becomes A plus 2D till A plus 20D. That is 693. Okay. Now if we use the summation AP formula, we'll be getting 2A, sorry, 21 by 2, 2A plus 20D equals to 693, right? Because we have 21 terms over here, that's why 20D. Okay. So this and this gets cancelled out. What we have got, 21 times A plus 10D equals to 693. So A plus 10D comes out to be 693 divided by 21. That is 33. Okay. Now what do we need to find over here? We need to find this. Okay. So this is, let's say, S equals to A1 plus A3 plus A5 till A21. Okay. Let's write down this in terms of A and D, right? So S equals to, this is A, this is A plus 2D, this is A plus 4D till A plus 20D, right? I can see that this is individually an AP with the common difference of 2D. Okay. So S becomes 11 by 2. Why 11? Because it has 11 terms. You can count that it has 11 terms. It becomes 11 by 2 multiplied by 2A plus n minus 1. That is 11 minus 1 into 2D, because we have a common difference of 2D over here, right? Now we have to find out this value, right? So this 2 and this 2 gets cancelled out. What we have got, 11 times A plus 10D. Okay. Now A plus 10D was 33, right? So this becomes 11 into 33. That is 33, 33. That comes out to be 363 as the answer. Okay. Now let's talk about geometric progressions. So GP is a sequence of numbers whose first term is a non-zero and each of the succeeding terms is equals to the preceding terms multiplied by a constant. Okay. In AP, what we were doing, we were taking a number, a fixed number, that is the first term, and we were adding a constant number, that is D, common difference D, to every subsequent number, and that's how we were generating an AP, right? But in case of GP, what we are doing, we are taking a number from starting, that is the first term, okay, and we are multiplying a number. In case of addition, we are multiplying in GP, and that term is called as common ratio, right? R is called as a common ratio, that is a constant number which is being multiplied to every consequent number, every subsequent number. Okay. So the first term would be A, second term would be AR, third term would be AR square, fourth term would be AR cube, and so on. And nth term would be AR raised power n minus 1, right? AR raised power n minus 1. This would be our Tn, general term, right? Now let's solve this question. Let A be the first term and B be the nth term of a GP. If P is the product of n terms, then P square is. Okay. So the first term is A. Let's say the common ratio is R. So B would be A R raised power n minus 1. Right. Now the question says P is the product of n terms. So P would be T1 multiplied by T2 multiplied by T3 till multiplied by Tn. Right. So P equals to, what is T1? T1 is A. What is T2? T2 is AR. What is T3? T3 is AR square till, what is Tn? AR raised power n minus 1, right? Now what we have to find? We have to find out P square. Now let's write P once again, but in a reverse format, right? So I'm writing this term as the first term, this end term as the first term over here. So we'll be getting AR n minus 1 multiplied by AR n minus 2 multiplied by AR n minus 3, right? Till at the end we have A, right? So when we multiply both of them, we get P square equals to A dot A R raised by n minus 1, right? Multiplied by A dot A. This is R raised by n minus 2. This is R. So the product would be R raised by n minus 1. Similarly, over here, we'll be getting A dot A R raised by n minus 1. Till the end, we'll be getting A dot A R raised by n minus 1. Okay. Now, if you take this A, this A, this A out of the picture, we'll be getting A raised by n, because we have n terms, right? This is A, this is A. Every single term is having A. So on multiplication, we'll be getting a raised power n, right? And this individual term is nothing but Tn. And what is Tn? Tn is nothing but b only, right? So this becomes b. This is also b. This is also b. And till the end, we have got b, right? So what we have got eventually, we have got a raised power n dot b raised power n. That becomes a dot b raised power n. Okay. Now let's talk about the summation of n terms in GP, and let's denote the summation as Sn. Okay. So Sn equals to T1 plus T2 plus T3 plus T4 till Tn. Okay. Now this can be written as A plus AR plus AR square plus AR cube till AR raised power n minus 1, right? Now let's multiply R in all the terms. Okay. So we'll be getting R times Sn equals to AR plus AR square plus AR cube plus AR raised power 4 till AR raised power n. Okay. Now if we subtract both of these equations, this is equation 1, this is 2. If we subtract 2 from 1, we'll be getting Sn 1 minus R equals to this and this gets cancelled out, this gets cancelled out, this gets cancelled out. So basically terms are getting cancelled out diagonally. So what we're left with, a minus ARn, AR is per n basically. Okay. So this becomes a times 1 minus R is per n, right? Now Sn becomes a times 1 minus R is per n divided by 1 minus R. So this is the summation formula for a GP. Okay. And now if we want to find out the summation of infinite terms in GP, then we have to start from the basic only. So Sn, as we found out, is a times 1 minus R is per n divided by 1 minus R, right? Now we want to make n as infinity over here, but there can be certain cases. So if we are making n as infinity and let's say R equals to 2, right? R is some positive number which is bigger than 1. In that case, eventually it would become infinity only, right? Because this term would become infinity, right? Regardless of what we're doing, this term would become infinity because R is 2 over here. And let's say R is 1 by 2. In that case, this term would become 0 because 1 by 2 raised power infinity would become close to 0, right? So we can ignore that term. So when we're talking about summation of infinite terms in GP, we're primarily talking about when R is a fraction. R is a fraction that is less than 1 and bigger than minus 1, right? When R is a fraction which is less than 1 and bigger than minus 1, only in that case we can find out summation of infinite terms in GP as a concrete number, right? Otherwise, in all the other cases, it's going to be infinite. Okay, simple. So the basic condition over here is modulus of R should be less than 1. That is a basic condition to apply the formula for summation of infinite terms in GP. Now when we have assumed that modulus of R is less than 1, we can assume that R is per n would be 0 because that would be a fraction raised per infinity. That becomes 0, right? So it becomes a times 1 upon 1 minus R. That is nothing but a upon 1 minus R. Now this is our summation infinity. Okay. This is only true under the assumption of this one, right? You cannot write down S infinity as a upon 1 minus R when R is something bigger than 1, right? You cannot do that. We have to write this condition. Only in this condition we can say that this is true. Okay. So today's lecture was till here only. So let's meet in the next lecture for GP properties and basics of HP. Thanks for watching.